Welcome to this puzzle session. Here is the problem. There's a flea on each square of a 5x5 board as shown. Each little square has a flea. Flea is some small insect which you can Google. At the press of a buzzer, every flea jumps to a square adjacent to it. So adjacent is in quotes, I will explain. So there is some, at some moment of time, a buzzer is pressed and then all of the fleas simultaneously jump to a square adjacent to it. And what do we consider adjacent? Horizontally and vertically adjacent. So we are not assuming, or we are not considering that diagonal squares are adjacent. So for instance, if suppose this is yours, flea somewhere here, then the 4 squares available to her in the next step are the ones as shown. So either horizontally adjacent or vertically adjacent. To this one, only these 2 are available, and so on. To this guy, 3 are available, 2 up and 1 left, and so on. So at the press of a buzzer, every flea jumps to a square adjacent to it. We want to show that some square is then occupied by more than one flea. So after the jumps have happened, we want to show that there will be some square which will house more than one insect. Very interesting puzzle. As usual, you're encouraged to pause the video before we look at what I'm going to discuss. And with that, now let us move on. So we will discuss 2 solutions to the problem. The first one is very short. It just requires coloring the chessboard. So you have this chessboard, you color it black and white, or in my case, purple and blue. And I have used a 3x3 board just to illustrate, doesn't change anything. The reasoning that we are going to supply will work for any odd cross, odd board. So yeah. So we have a 3x3 board and the same problem. Now the thing is, initially there are some flea, exactly 1, 2, 3, 4, 5 flea on the purple squares and 4 flea on the blue squares. But the crucial observation is, once a flea jumps, it necessarily changes the color of its square. So the purple square flea will have to go to a blue square, and any flea on the blue square will on the next step has to go to a purple square. So every flea is changing its color in the sense that it is changing the color of the square it is on. But since there are 5 purple squares and only 4 blue squares, the 5 purple fleas will now become 5 blue fleas, but there are only 4 blue squares. So if you want to invoke the pigeonhole principle, or just common sense tells us that there will be at least 2 flea on one blue square, on some blue square. So that finishes the proof. I don't see any point writing all of this down. I hope you understood. You can reason exactly the same way for 5x5 or 7x7 or 9x9 and so on. Okay, so this is solution 1. Let's go to solution 2, which is a bit longer but maybe a bit more natural, at least to me. So again, I'll illustrate the point via a 3x3 example. So to each square, we will make or associate a dot. Okay, and now what we have is we have a flea here and it jumps to some adjacent square. So it gives us so we will draw an arrow to record that. If the flea jumps to the right one, the arrow will be drawn this way. If it jumps to the bottom one, the arrow will be drawn this way. Similarly, suppose the flea on this jumps right, then we will draw an arrow this way. If it jumps down, then arrow this way, and so on. So what we will see is that there will be arrows drawn from every square to either left, right, up, or down. And let us make the assumption that after the jumps, no square houses more than one flea. Meaning we are assuming on the contrary to what has to be proved. And then we want to we want to produce a contradiction. All right, so the thing that we just developed, that is called a directed graph. Basically, to each vertex here, we have an arrow coming out of it. And each vertex has exactly one arrow coming out of it. You have a flea here, it jumps to exactly one guy. The flea cannot jump to 2 different squares simultaneously. So this is a very simple observation. Every vertex has exactly one arrow coming out of it. But by our assumption that no square houses more than one flea, it follows that every square has exactly one arrow coming into it. Right? Uh, this assumption only says that every square has at most one arrow coming into it, but since the number of arrows going out is same as the number of arrows going in, we conclude that every vertex has exactly one arrow going into it. Okay? So both these things, maybe it's better to put them somewhat closer because they are of the same vein. And now, note that because of the above two, in fact, just by the first one, we can say that every vertex lies on a cycle. So what is a cycle? A cycle is you go this way, this way, this way, this way. So this is a cycle, basically a closed loop where you are respecting the arrows. You are not allowed to go against an arrow. So that is what we mean by a cycle in this context. So why should everything lie on a cycle? Basically, you start somewhere. You follow the arrow, you follow the arrow, you follow the arrow, wherever it takes you. And it has to come back to where it started. So yeah, I maybe misspoke a little bit when I said that this alone implies this. No, but we need both of them. So yeah, you follow the arrow, wherever it takes you, just keep following the arrow. And at some point you have to revisit a vertex you have already visited because there are only finitely many vertices. So you will revisit a vertex at some point, but you will not be revisiting a vertex that is in the middle. Because if you do that, this one in the middle is getting two things, two arrows inside it, two arrows to it. But we have already seen that by our assumption, every vertex has only exactly one arrow going into it. So once again, just keep following the arrow. Wherever the arrow takes you, you will revisit a vertex at some point. But if you revisit something in between and not at the starting, then this point will be contradicted. Okay, so every vertex lies on a cycle, and in fact what we have done is that no vertex lies on more than one cycle. Because if that happens, then either this or that will be contradicted, or both will be contradicted. So every vertex lies on a unique cycle, in fact. Okay, so this shows that every vertex lies on a unique cycle. And just note that every cycle has even length. So you're either going down or right or down or left and so on, and coming back to wherever you started. So there has to be an even number of steps, even number in the horizontal direction, because if you just record the x coordinate, you're coming back here. So there must be even number of movements in the horizontal direction. And similarly for the y coordinate, there must be even number of movements in the y direction. Even plus even is even, and hence every cycle has even length. This is a crucial observation. And now if we put everything together, we see that the number of vertices must also be even, because every vertex lies on a unique cycle, and every cycle has even length. So the number of vertices must be even, but that's a contradiction because the number of vertices is odd, because the number of vertices is, in our example, 3 times 3, or in the question 5 times 5, or 7 times 7, or whichever. So therefore this is a contradiction, and we are done. So those are two solutions to the very nice problem. I hope you were able to enjoy this session. As usual, like, comment, share, subscribe, and I will see you next time.